Welcome to part 4 of this video series. This time we are going to look at the thermal performance of the final assembly of the system, and we'll do a bit of a recap on the electronic components that were chosen. First of all, I want to share some news. This is a first for our channel, so it's the first time that the videos have been recognized by a media outlet. So Fanless Tech was kind enough to feature us on their blog. So thanks a lot for this. I'm very excited about that. But now let's get right to it. This time we want to look at the thermal performance of the final assembly of the NAS system. So I did a 2.5 hour test sequence run and recorded a lot of data, and we'll be going over this step by step. As you can see here, the test sequence is divided in 4 parts. There's part 1, part 2, part 3 and part 4. We are going through all of those separately and interpret what is going on. One thing that we can see here on the overview already is very relevant. What was recorded here on this level, these individual brown dots that we can see here, is the room temperature. And that orange line that we see there measures the air temperature within the chassis. So just in the location where the X570 chipset is located, I put a temperature sensor just into the air such that it can measure how hot the air is going to get over there. This relates to the measurements I have done in part 2, where I made assumptions on the air temperature around the X570 chipset. So now with this measurement we actually have a real value. At that time I was measuring under room temperature like 88 degrees on the X570 chipset. And I was assuming that the air inside the chassis would be 10, 15 or 20 degrees higher. Adding these values to the X570 chipset temperature is what led me to believe that I will be exceeding the 100 degrees on the die, and I guess it will be mandatory to define a custom heatsink for the X570 chipset. So here actually now we can see a real value. And actually this was even worse than I assumed. So here, when doing the final measurement runs, I was seeing a temperature difference of 22 degrees Celsius. So meaning if I would not have taken any action cooling the X570 chipset, in that situation we would be at least at 110 degrees on the X570 chipset. So for sure this would not have worked. So other information that we can see on this diagram, so we have the pink line here. This is again the power consumption of the I/O die. And we have here this accumulation of purple dots, which is the power consumption of the CCD. The lines which we can see here on top, blue and green, are the temperatures of the dies. Basically the blue line is the T-die temperature, which is the relevant one that we need to look at. We can see if we are hitting 90 degrees here, this is getting into territory where the CPU is starting to clock down because it gets too hot. And ideally we don't reach that. We can already see here in the beginning, here we have reached 90 degrees, and here we have even crossed the 90 degrees. So this now is a zoom into the first part of the diagram. What I was doing there is I was starting from cold state. Cold state means the system was powered off and then was powered up, and then we started to do the first test. That's the cold state. So meaning the chassis and the walls and everything had not yet heated up at all. So if you're going back to the beginning, what was set up as goals for the NAS system to achieve? So first of all, we wanted to be able to compile Linux kernels endlessly. And the second part was we wanted to push in and out data at a sustained 1 GB per second. So in the sequence that we are looking at now, I will basically be testing those. What we can see here, this is a single Linux compile. So we are at 72 watts. We started from cold state. The Linux compilation was running here in that period of time, and we were reaching in total like 76 degrees on the die. So this was the second phase of the test. I started the Linux compile just in a loop. So compile, clean, just in an endless loop. And so we can actually see that the graph here is like split into individual parts. So here where we have these small dips, this is always when it just deletes what has just been compiled, and then here it's working again. So during the deletion phase, which is very short, it has a chance to cool down a little. So what we can see there is after compiling the kernel 17 times, we are hitting 90 degrees. So we are in a situation where the system is under full load for this is like half an hour until we are hitting the thermal limit. So now if you're going back to the goal definition saying, well, I wanted to compile the Linux kernel endlessly and not run into a terminal throttling situation, well, strictly speaking, this is not achieved, because after half an hour, we are already in trouble with the terminals. But still, then, how realistic is it to actually compile the Linux kernel like that 17 times in a loop? Well, not really. You would compile, then you need to do some coding, and then you recompile, and when you recompile, you're not recompiling everything, but only the things that you have changed. So this scenario is a bit artificial, but I have still defined this in the beginning, just to have the challenge high enough. This was part 3 of the test phase. This is actually split into 2 parts. We can see there's here and here. Here we were running like NAS functionality, so to say. Basically over Ethernet I was accessing the NVMe inside the system and was executing heavy transactions over NFS. So just using DD to pump data into the system. Here we can see that the system is operating at 53 watts, and from a terminal point of view we are stabilizing here at around 79 degrees C. So using the system as a NAS under load, while we're not expecting a real problem. Another thing that we can see here is, so I noted down the X550 and the X570 temperatures that I observed again over APMI. So the X550 is the 10G Ethernet, where a custom heatsink was designed. In this scenario, this was operating at 63 degrees Celsius. The X570 chipset was operating at 75 degrees Celsius. So the cooling solutions that were shown in the previous part of the video series were effective. So afterwards, this one was still running. I just added the kernel compile loop again. And as expected, the same thing was happening. So after a while, we are hitting the 90 degrees Celsius again. So this is the last part of the measurement. So this was the 4th phase that was shown in the previous diagram. So here I was saying, I will wait for 5 minutes. I compile the Linux kernel and I delete what I just compiled. Then I wait again for 5 minutes. I compile, delete. Wait, compile, delete, and so on. So that the idea was to say, let's be a bit more realistic, to say, because for sure I might need 5 minutes in between kernel compiles, to actually do my file modifications. It's still not realistic in a sense that I do not have to recompile the entire Linux kernel, but only a part of it. But still I wanted to see what happens in this case. And what we see is that basically the system is always cooling down. So here in that waiting period we are a bit going down, then we're recompiling again, it's actually ascending a bit. So we are always staying just below 90 in that situation. So of course here again we are starting from a hot state. All the tests that I have shown before were run immediately before that, and afterwards this was run. If we would have started that from the cold state, the diagram would look very different, of course. Here I have 2 screens showing the chassis temperature during that run. So I was actually having the infrared camera pointed at the chassis just to find out in which order of magnitude the temperature of the chassis is. We can see that the lower part is significantly hotter than the upper part, which totally makes sense. So we have routed all the heat pipes from the CPU basically to the walls on the lower part, and here this one wall, which is a little bit warmer, is the one which has the heat pipe from the X570 chipset. So naturally this is only a few watts compared to this is where a lot of action happens. It is natural that this one is much hotter than that. So in terms of absolute values, it is very difficult to measure how hot the walls actually are. If you want to measure that with a high level of precision, so we would have to put a hole inside the walls and put a temperature probe in there to really know how hot they are. I did not want to do this just because the walls are actually looking so nice. I did not want to interfere with them at all. I did not want to risk damaging them. So all I did was basically looking with the infrared camera. So but with infrared, the temperatures observed always depend on while having the correct emissivity set on the infrared camera. So these values here, I'm not exactly sure how precise they are, but there's an order of magnitude of 50 degrees that I see here. Well, here it captured 46.1, here it captured 49.2 degrees Celsius. When touching it like that, it felt quite hot, so it was uncomfortable on the fingers. So we really have accumulated quite some temperature there on the walls. Previously, we have been looking at the terminal performance under the artificial load, compiling the Linux kernel in a loop. And there we have seen that after half an hour, we have reached the 90 degrees where the CPU starts to throttle. So I was wondering, how does the temperature performance look like in reality, so under a real use case? So for this, I was actually sampling the same data like I have shown before over a period of 6 weeks. So this was basically between the time of filming the previous video until filming the current video. And so the coloring here is the same like before. And this here was the time when I did the benchmark. So we can see actually here a glitch quite high. But what we can see here, this is how the thermals look like in reality. So we have here a few spikes and up and downs. We have here a few, here a few, here a few. This is typically then scenarios where I was working and doing something with the system. So something beyond the usual. But it's clear that, I mean, none of what is visible here is in an order of magnitude like we have here on the benchmark. So meaning, well, strictly speaking, so the system has not reached the goal that was defined originally, but for practical use case, the thermal solution is good enough. Here again is a plot of temperatures. This one is again over the same 6 weeks period. But what I was logging here was all the temperatures of all the flash devices. So all the SSDs in the system, all the NVMe devices in the system. So just to be sure that they are operating within reasonable conditions. What we see here as higher temperatures are the SSDs, and what we see there as lower temperatures is the NVMe. So we clearly can see that the ASUS NVMe carrier, even without turning on the fan, is cooling the NVMe very well. Also, the onboard NVMe with that heatsink that I showed in the first part with a heat pipe is more than good enough. So we are reaching here like 40 to 45 degrees. This is not a problem at all. However, it's interesting to see that the SSD temperatures are actually higher. So we are reaching some peaks here of like 70 C, and here at one point in time even 75 C. So I still remember what I did on that day. I was actually setting up a backup server which was taking an image of everything that is on the NAS. So it's natural that here we have a lot of load on the SSDs. But still it is a bit surprising that the temperatures of the SSDs have so high spikes. What I think what happened there is, in total I have 8 SSDs in the system, and I stacked them all on top of each other, one of them touching the other. So if I had mounted those with some spacing in between such that we have more surface for the heat to evaporate, it would probably have been better. So whenever I have a reason to do maintenance on a system, this is maybe one of the things I'm going to try and improve. However, we are still within 70, or in a more worse situation at 75 degrees C. This is still not the temperature range to be worried about for the flash devices. But wait, isn't there something strange? Why are we hitting the 90 degrees on the CPU? If we remember, there was a test in the previous part of this video series. So I had a 5950 here, routing heat pipes here to the front wall, then routing heat pipes from the front wall to the side wall, and I had here these bent heat pipes which were routing heat to the third wall. And there we see that, well, here we have 72 watts, that is exactly the same wattage that we had before, and here we are at 80 C. And I was saying at that point in time, well, this is the NAS worst case, so I'm assuming that the cooling here will be fine. But what we just saw is now on the actual assembly we hit 90 degrees. So something does not add up here. This image I have also shown already in the previous part, and I was explaining how the CPU packages are structured internally. So the 5950, which was from the previous part of the video series, actually has here an I/O die and then 2 of the CCDs up here. So this is where the cores are, and this is actually where the actual load happens. While what I put here in the NAS is a 5600X. This one has only a single CCD and a single I/O die. And at the time, to do the benchmark with the 5950, I was basically like throttling it such that it would consume the same power like the 5600X in that scenario. So one difference that we have between the two systems is actually the throttled 5950 has the heat load spread out over 2 CCDs. So when running the 5600X, I have 65 watts here and 7 watts here, roughly. On the 5950, we have like 32 watts here, 32 watts here, and 7 watts here. So we have more surface available below the CPU package to dissipate the heat onto the heat spreader. So if we're doing the math, We have 85 square millimeter for one CCD. We have 128 square millimeter for the IO die. So the 5600X has a total of 213 square millimeters of surface to transport the heat, and the 5950 has 298 square millimeters to transfer the heat. And well, that ratio gets even more severe if we consider that most of the energy is actually consumed here and not here. So this one is only consuming 70 watts, while here on this level we have the 65 watts in total. So effectively the 5950 has almost twice the surface available to dissipate the energy compared to the 5600X. So now the question is, how can we prove that this is the effect that we're experiencing here on the assembled NAS system? From the previous part of this video series, you might remember the experimental PC. So this is a homemade passively cooled chassis that I'm using just to experiment with the technology and to learn about behaviors. So compared to last time, I've updated the heatsink here on the back. This is like twice the size of the heatsink that was installed there before. This I did just to be sure that the CPU can dissipate the heat also at up to 125 watts in that system. So I was using that system. First I ran it with a 5950, throttled again to the 72 watts, and then I downgraded it to a 5600X. Running it without throttling, so such that it would also consume 72 watts, and then doing a comparison of where the temperature would settle. In this chassis, the entire system can dissipate 125 watts, so for both scenarios I was within bounds, so I was not heating the 90 degrees anyway. So this was the first test run that I did, just to be sure that the cooling solution here can dissipate sufficient load. In this scenario, a 5950 was installed, and I throttled it down to like 125 watts. So this is already pretty close to the maximum that the CPU does. If running it without constraints, it is running at somewhere between 140 and 150 watts. So about 125 watts was like the limit that I found that I could extract without airflow using that larger heatsink. What we want to do is we want to compare at same power in the same cooling solution a 5950 versus a 5600X. For the first experiment I was running the 5950. The power was limited, so in this test it was consuming 73 watts, and we can see that on an M' load it stabilizes here at 60 degrees. As a next step, I was downgrading the system to a 5600X. This one was run here without any restrictions, so I just left all the settings regarding power and clocking at auto. So it was just decided by the CPU and the mainboard what is going to happen. So we can see that in this scenario, from a power point of view, we are pretty much at the same level. So we are looking again at 73 watts. We can see that the temperatures of the dies are climbing up. It is interesting that it does these steps here. So I'm not exactly sure why this happened. For some reason the CPU decided to do that, but over time it actually stabilized. So here it was stabilizing at like 70 degrees. So out of curiosity, I was then, after the M' was completed, I was running a game on it. So I was actually running Cyberpunk here, and the temperature here climbed a little bit more. What we can see is that it was actually quite stable. We are at 72 degrees in that scenario, and the power, well, the spread has gotten a bit higher, but all in all the level of power is still the same in total. But what's interesting is, if you're looking at the slide from before, the 5950, when throttled, was stabilizing at 60 C, while here we are at like 70 to 72 C. So the impact of having one or two dies, or having more or less surface, clearly has an impact on the thermal performance of the system. You might have heard me saying in the previous parts of the video series already a few times, TDP is a number that does not mean too much. And here we have just demonstrated actually why I think this is the case. We have seen that from a thermal point of view, at the same level of power consumption, the 5950X behaves quite differently than a 5600X. So when looking at a thermal solution of a computer, what we actually need to look at is the full chain of cooling. So with a full chain, I mean like from the place where the heat is generated, meaning inside the die, from there to the heat spreader, from there to the cooling solution, then to the outside, and so on and so on. You can see real examples for this, for example, when looking at the Noctua website. they are not specifying for their cooling solutions what kind of TDP those cooling solutions can cool. Now what they have is like a list where you can enter your CPU type, and then you enter the cooler that you want to buy, and then it will tell you for this CPU is the cooling solution good enough or not. So with Noctua then we are typically talking about airflow based cooling. So here it will then depend also on the chassis, on how well it can ventilate air, and so on and so on and so on. So lessons learned: when choosing a cooling solution, always look at the full chain. Always look at the system as a whole to choose the right one. A bit of a recap on the hardware choices. So I'm only going to talk about those where I had something interesting to say. There was no problem with the SSDs, the NVMe carrier, and the NVMe, everything was just running fine. However, the mainboard is a bit interesting. I think it's a mainboard that is very suitable for a NAS, just because it has a lot of I/O that is useful for NVMe and SATA. The Occolink connectors, we can in total connect 8 SATA drives, and with NVMe and the carrier we can connect a total of 5 NVMe drives. So we can attach a lot of storage to it. However, it has a few peculiarities. So one thing is that what I found out that it is very important to follow the list specified by the manufacturer when it comes to choosing the DDR memory. ASRock actually has on their website a list of supported RAM modules for the device. And I started off with those and I had no problems. At one point in time I had a few other ones, and I was just experimenting with them, and well, obviously the system was running. However, it was not stable. So when you're using M-Prime, you can configure it not just only as a benchmark use, but it can actually test your system. So it would detect if you have instabilities, if you have calculation results which are not right. And when changing the RAM to those modules which are not on that list, after a few hours of running, I had actually errors. Another thing is also that the RAM that I bought, which was on the list from ASRock, actually says it's DDR4 3200 MHz. But in fact, when putting them into the main board, they are only detected as 2400. And I did not find any way to actually make use of the 3200. So this is likely a bit of a bottleneck for the CPU. Another thing that I found with that mainboard, even though officially listed it supports a 5600X and a 5950X, I never had any problems with the 5600X, but with the 5950X I had situations where sometimes the mainboard just wouldn't start, or it would just sporadically shut off. So my suspicion is there that the DC-DC conversion electronics on the mainboard are actually not suitable to handle the power levels required by a 5950. I checked a bit the web, and I've seen many people with that observation. Myself, I've also tried this. I have multiple of those mainboards, and I have also more than one 5950X, and I had the problems basically with all combinations. So for me, the point seems to be that the 5950 does not really run stable on that mainboard. 5600X, however, I can recommend without any troubles. I do not have a 5800X or a 5900X to say how they behave in that mainboard. So from a power point of view, they are just between the 5600X and the 5950X, but I could not do any tests of those because I just don't have them. Even interesting, so when running the 5950X, I could actually limit the power to that of a 5600X, and also in that situations I observed the instabilities. So it is not clear for me what is really the point. At home I do not have the means to investigate this any further. However, if I combine my observations and what I can research on the web, I will conclude that there is some kind of problem with the board with the high power CPUs. Another thing interesting to note when using that board, and this is really critical, is that the spacing of the holes which are made to mount the cooling solution, even though it's an AM4 socket for AMD CPUs, obviously, the hole spacing here is the one for an Intel CPU. So it's from the LGA 115X sockets from Intel. It is not a big problem. It's just very important to know when choosing the cooling solution. So also for this, it is important to research on the web whether the cooling solution that you want to put is actually compatible with that mainboard. A generic AM4 cooler, or the generic cooler that comes from AMD with the 5600X, you cannot mount on that mainboard. Another very helpful element on that main board is that on the back side it actually has like a stiffening plate below the socket. So it seems to be made out of steel, and it covers the back, the entire area here, and actually the threads. And actually here it has M3 threads to mount the cooling solution. So on the one hand, this makes sure that the PCB does not get bent, and on the other hand, it is very convenient that we already have threads in there when screwing in the cooling solution. I found this is a very clear plus of that mainboard as well. So now let's move into my office, build the thin client, and then see how I'm actually working with that system in reality.
So here we can see the case for the Raspberry Pi 4. It works based on the same principle like the Streacom chassis, meaning actually it's the case itself which serves as a heatsink for the electronics. We can see those elevations here on the case. They are made to interface directly with the electronic components on the board. Some thermal pads are provided to put in between. If we turn around that part, we can see that the surface here has some elevations. They are done in a way such that the surface is increased and like this more heat can be evaporated in the environment. So all in all, that case works in the same way like the Streacom DB4 in principle. It is the case itself which serves as the heatsink to extract the heat from the electronic components. I have a few of those cases in use at home with Raspberry Pi 4, and they just work perfectly to extract the heat from that device. So here you can see the Raspberry Pi in action. Due to the limited computing power and also the limited graphics power of the Raspberry Pi 4, I'm only using a terminal to log into the NAS to work there. Nonetheless, the Raspberry Pi is good enough to open a web browser, so you can use it to look up documentation that is relevant when programming. So all in all, for me, that's an excellent setup for developing software. I can work in a completely silent room. There is no disturbance whatsoever, and at the same time I'm getting the compute power of Ryzen 5600X. So that's just wonderful. So what is going to be next? I consider the hardware configuration of the NAS final. There are a few shortcomings that I have outlined already before, but still it is good enough, like we have seen, to actually do its job. So in terms of NAS, my plan is to continue then talking about other aspects of the system, what kind of software is going to run there, storage, network, and all those questions. Nonetheless, I find working with passively cooled systems very interesting. So I intend to continue on that line and actually build up other systems. A small peek, you can see some electronics already here, but I will not tell yet what is going to be the plan. So thanks for watching. I'm looking forward to welcoming you all again in part 5 of this video series. So if you like the work that I'm doing, please subscribe and hit that bell down below. Thanks a lot, and bye bye.